Welcome back to our ongoing look at inverse trigonometry. See, up until now, we've been looking at it in one very specific direction, right? I had the notion of going around the unit circle some amount in some direction, ending up at some terminal point, getting some x and y coordinates, and using those to define cosine, sine, tangent, and so on. And that's what we've been doing so far. But now I've put forward the idea of doing it in reverse. Instead of knowing where I'm going and asking where I end up, suppose instead I'm given the destination. I know where I am, and the question is, how did I get there? And that's what we were looking at last time, right? For instance, I asked, suppose I know that sine is a half. Where am I? And the bad news is there's two answers for that. If sine is a half, you could either be here in the first quadrant or here in the second. Also, if you said, I know that my cosine value is 0, for instance, well, that means you're either up here or right down here. And tangent, if you told me tangent was 1 and that's all you knew, well, I couldn't tell you exactly what position you're in because you're either here in the first or here in the third quadrant. There's that ambiguity that arises. It's not truly possible to completely and totally undo a trigonometric function and know exactly where you started. And that's going to be fine, because what we will be able to do today is still be able to get some useful information. So let's get to that. So saying it once again rather formally, given known outputs of some function, what was the input that had to go in to find it? So for instance, if I knew that my output was 0, then what was the value that went into sine of x to have an output of 0? And yes, there's infinitely many such values. 0 would work, pi would work, 2 pi would work, 4 pi would work, and so on. All those integer multiples of pi would all have a sine value of 0. But at the same time, even though there's infinitely many possibilities, they do still have some nice relationships that we'll look into. So, to kick us off today, we will start briefly mentioning how we would invert a function. So this is more from the pre-calculus algebra side of things, the 1710, where you have a function like f of x equaling x cubed, where you take all the inputs and cube them, and that's your output. So 3 goes to 27, 1 goes to 1, 0 goes to 0, 4 goes to 64, that sort of thing. Well, let's suppose instead I knew the output and asked the question, what was the input that gave me that? For instance, what if I said that my output was negative 27? Well, then you would still be able to tell me what input did that, because negative 3 to the third power is negative 27. So we can invert a function such as this one. And the way you could do that, if you remember from your algebra courses, is you could first rewrite the y's for x's and the x's for y's. So f of x equaling x cubed becomes g of y equaling y cubed, or x equal y cubed. You could then solve for the new x, or the new y in terms of the new x's, get y equal the cube root of x. Your inverse function will be y equal cube root of x, or g of x equal x to the 1/3 power. So that's how we create inverse functions in general. And we like those because they undo functions and tell us what we did in the first place, or what would have been done in the first place to produce those outputs. And yes, it's going to work out to be that these functions have symmetry across the line y equal x, and also if you were to compose the two functions, you would get the equation y equal x. So let's hold on to that, let's hold on to this line, and let's start inverting some functions. Specifically, sine of x. Now sine of x is a function, it's defined over all real numbers, but if I were to swap x's for y's, y's for x's, or reflect it across that line y equal x, I end up with this guy right here, x equals sine y. Now this thing is not a function. It fails the vertical line test really, really badly. It's defined infinitely many places whenever it's defined once. In fact, you could have already been able to tell me that it would not be invertible because the parent function, y equals sine x, fails the horizontal line test. But however you choose to do it is fine, because at the end of the day, this function, y equals sine x, does not invert into a function. But that's going to be okay. Because what we're going to do is not define our inverse function for all of sine, but rather for just one tiny piece of it. This piece right here. If we restrict the domain of the sine function to be just between plus or minus pi over 2, just between plus or minus pi over 2, we do now have a function that is invertible. And there it is. That is the graph of the arcsine function. Not that we need to remember that necessarily, but we do need to remember that it's only going to work for values between plus or minus pi over 2. So let's circle back to this now. Arcsine has to be defined between plus or minus pi over 2 because that will give us a function. So we take all the inputs from sine, and sine of course gives you anything out between plus or minus 1. So the domain of arcsine, which we write either as arcsine or as sine inverse. Normally this negative 1 exponent represents reciprocals, but in the context of sine and cosine and tangent, it's actually inverse, which I know is a little complicated too, but so it goes. But anyway, that takes all the outputs of sine, anything between plus or minus 1, and returns the angle or the value between plus or minus pi over 2 that produces that output. So for instance, a few quick examples here to wrap up this video. If you were looking at the arcsine of 1/2, that is asking the question, what is the number between plus or minus pi over 2 that gives me sine of that number equal to 1/2? Well, we kind of think about that for a bit. We draw maybe the western hemisphere or the eastern hemisphere of the unit circle. Let me show you what I mean here. Right, if here is our unit circle, seeing as how plus or minus pi over 2 is only this half of it, we look just at that thing, and we ask, okay, so where here am I going to have a sine value of 1/2? Or where here am I going to have a y coordinate of 1/2? And the answer is when t is pi over 6. And that's the only value we get out. Yes, I know that sine of 5 pi over 6 is also 1/2. I know that sine of 13 pi over 6 is also 1/2, and so on and so on. And negative 7 pi over 6 and negative 11 pi over 6 are also going to be 1/2. But arcsine only gives values between plus or minus pi over 2. And the only value between that range on that interval that does what we want is pi over 6. And so, that is the answer to the question, what number gives me sine t equal to 1/2? Therefore, the arcsine of 1/2 is pi over 6. And just a couple more here to round us out. The arcsine of negative root 2 over 2. That's asking, where do I go between plus or minus pi over 2 to have an output from sine of negative root 2 over 2? And the answer is down here. It is in the fourth quadrant, right? Specifically, when we go pi over 4 in the negative direction. So negative pi over 4 is the value that we want. That's going to be what arcsine of negative root 2 over 2 is. Arcsine of 0, that's asking, well, where do I go on the unit circle to have sine of that spot equaling 0? And the answer is nowhere, because sine of 0 is 0. So arcsine of 0 is 0. Arcsine of 1 is pi over 2, because that's where on the unit circle I go to have a sine of that value to be 1. And lastly, arcsine of 2 is undefined, right? Because there's nowhere on the unit circle I can go, let alone just on this half of it, but anywhere, where I'm going to have a sine value of 2. Because, well, the unit circle only goes from plus or minus 1. So arcsine of 2 is undefined, and that's more or less how we do all of them. For all the arcsine evaluations, we just ask ourselves, where on this half of the unit circle, am I going to have the y value, or the sine value, being what I'm trying to find? And that angle, that position, that number is what arcsine is going to come out to be. So that's it for this video. I've got a quick question here to ask you, and then we will get into the next, and we'll talk about arc cosine and arc tangent, and that'll round us out. So, have a good one.